I'm the guy who created Fly System. That's the package that's used within Laravel to do anything file system related. When I spoke here last year, it was a milestone for Fly System because we just then hit 2 million downloads. Like now, barely a year later, like in a couple of days, it's going to be a year later. And it's actually so damn close to hitting 10 million installs right now. So thank all of you for that, for your trust in that open source package. So thanks a lot. Right, I should definitely keep this open. All right. A good friend of mine, his name is Ross Tuck, he says, always start off a talk with a quote. So here's mine. Everything and anything that can be a problem will be a problem at scale. I've heard this before. I tried to track down the source, but couldn't find it, but it was definitely smart people. Who recognizes this piece of regex? I see one hand up. I see a shy hand up. Okay, so I'm counting 1.5. All right, this piece of regex has a problem, but this is really, like all the Unicode stuff is actually a little bit weird, but actually this regex has the same problem. This piece of regex has brought down one of the sites that you probably frequently use, which is Stack Overflow. Stack Overflow had a post on the website, which consisted of a character, 20,000 spaces, and then a character. If you know the internals of how regex matches their stuff, it goes something like this. It goes to, well, it's in reverse, so it goes to the first char. It sees, well, it's a character, so I'm matching that. Then it goes ahead and sees a space. OK, that's good. Goes to the left, more spaces, and it does that, and it checks that every time. So for 20,000 spaces, it will continue to recheck that assertion. And at the end, it wants to see the end of a line. But there's not the end of the line. After 20,000 spaces, there's a char. So what does it do next? Well, that first char and then a space didn't match. So I'm going to start from the second char, and then I'm going to walk all the way down 20,000 spaces again, -1, and then it sees a char, so it doesn't match yet again. Well, guess what it's going to do next? It's going to do that same damn operation for all the 20,000 spaces that's in that post. This, in the end, resulted in 200 million operations. So that wouldn't have been a problem, would it have been that the home page was serving that particular post, where that operation was actually executed. Coincidentally, that home page was also what was used behind the load balancer to see if an API node was healthy. Because every API node was doing 200 million operations, nobody could serve web pages anymore because they didn't match the health check criteria anymore. As I said, even the smallest thing can be a huge problem at scale. So what am I going to talk about in this talk? This talk is going to be a high-level overview talk about scaling. There are some pieces where I will go in depth, but mostly I'm not going to talk about Docker. I'm not doing virtualization, because that's a solution to a problem, and I'd like to talk about the problem. So what I'm going to talk about is resource management, here and there a bit of caching, and then see how infrastructural scaling can help. And it all starts with our application. And our application has certain traits. For instance, it needs to perform. It needs to be available, of course, because people want to use it, but it shouldn't be just normal available. it should be highly available, right? That's what we want. And when things go bad, we want to have a system that deals with that as well. And also, we want it load balanced. Why? I don't know. Because my colleague Bob told me, and he seems like a smart guy, so I better do it. But it all starts with our app. And mostly, that app starts in a box. For every development project, mostly like either you have a Vagrant box or whatever, or you have your own dev machine, that's one box. And for a lot of PHP developers out there, this box used to be a shared hosting box. So shared hosting is one of those cases where you know that sharing is caring does not apply. It's mostly like a dictator telling you, well, everybody's going to run PHP 5.1 and that's it. But then later on in our development career, we have our own box, whether it's, again, your Vagrant box. But this time, there's something different about this box. This box is an open box. And what tends to happen when boxes are open, you fill it with stuff. So this box, over time, accumulates all these tools, all these languages, all these things that get installed in the system. And for the longest time, we're super happy with this box. But this box gets older and older. And after a while, all these things kind of, begins to fall left and right. So after a while, this box kind of, starts acting weirdly. So, and if you continue on this path, after a while, like, what's in the box? But it all starts with this one box. And everybody's heard about either horizontal scaling or vertical scaling, and vertical scaling is not what we want to do. We want to do all horizontal scaling. So from this one box, we somehow have to get here. So, but yeah, so what's the problem? The problem that we're addressing is a resource problem, like oil. Well, oil is a resource, but it doesn't really apply, because if you use oil, you burn it up, it's gone. It's more like renewable stuff, like wind energy. It just keeps on coming. And what are the resources that we have to deal with? Well, RAM. Okay, RAM. So that's memory. And when you hit the limits of the amount of memory that you have, you can say you're memory bound. That means the execution speed is determined by the amount of memory required to hold the data. The other part is CPU. So if you're constrained by CPU, like the number of operations, like for Stack Overflow was the case, you can say that your execution speed is determined by the speed of the CPU. So that's CPU bound. But there's another one, and that has to do with time. But not just time going by, it's when time is slow. It's basically when you're waiting on stuff. That's like with API requests. You just, you send the request, and then you're basically sitting there until the response is back, and then you continue and do stuff. So when that's the limiting factor, you can say execution speed is determined by the time of waiting on input and output. So that's I/O bound. And it's quite easy to see that all these things are constraints, and that's not nice because we don't want to feel constrained. But it's also functional. A method of preventing spam is actually a protocol between the sender and the receiver of a given email, and they have a contract. The contract says, I want you to perform function X with payload Y and pass me back the result. And because the computation of that output is resource, either CPU expensive or memory expensive, it's going to take a lot of time for that sender of the email to actually perform that task, but checking the output is relatively simple. This makes sure that the cost of sending spam goes up, and it might not be profitable anymore to send the spam. So we're actually, there are benefits to these things. That's nice, but, what's the problem? Well, the problem is, we've got a game console, and we can play with up to 4 players. So everything is pretty nice. When we're like 1, 2, 3, we're pretty good. A fourth comes along, still good. But as soon as little Johnny enters the room and is the 5th player, he's going to throw a tantrum and throw spaghetti against the wall, apparently. So for us developers, this kind of looks like this. Or at least, that's what it looks like for them. So how can we deal with resource problems? Well, there's 2 main strategies. Either use less or buy more. So those are basically the only 2 options that you have. Well, let's illustrate this by looking at a little PHP script that consumes a little memory. What the script does is totally irrelevant. The only focus is that we see how a system reacts when we consume memory. So here we're going to pretend that the copy operation does not exist. So we're going to copy a file. First off, we're going to define a source and a destination. The source is always going to be the same file. I've created a file with just 40 MB of useless data. Then for each request, I'm going to create a temp file where I'm going to write to. So temp name, because the E was cut off because naming is good. And then I'm going to use those locations to use a shared lock to read the file into the contents variable, and then I'm going to put that content in the destination using an exclusive lock, so I know that nobody else is writing to this file. Lastly, I'm going to do some cleanup, so we're going to unset the contents and unlink the destination. What's funny here is because we read the entire thing in memory, is that you can say from the first time you see contents to the last time you see contents, we've got the full file in memory. So we're actually consuming the whole 40 megabytes. Well, that's nice, but let's see how this actually does stuff. So for this demonstration, I've created a Vagrant box with very little memory and just 1 CPU. So it's really narrowed down on resources so we can see the clear effect. So what we're going to do is we're going to create up to 500 requests to this Vagrant box with a maximum concurrency, so side-by-side requests of 100. So at most, at a given time, you have 100 requests hitting your application simultaneously. And we're going to see what happens. Well, it's pretty brutal because that Vagrant box definitely doesn't hold up. The execution time is ridiculous, and again, the box was deprived of memory and CPU. But there are also a lot of failed requests. So you can see almost like 1/5 of all requests failed. And that's a staggering amount. Also, we only have about 3 requests per second. Like if you had to tell your boss, well, we can do up to 3 requests per second, you might need to start looking for a different job. And the time per a given request, well, you can basically do the math. But there's another metric here. You can see that the first 50% of all requests came in or were executed within 34,000 milliseconds. The slowest request was 42,000 milliseconds. So there's kind of a gap here. OK, so let's optimize this. Well, now we're using streams, so we're using the fopen functions for reading and for writing. We're going to ensure that we have the same kind of locks that we had in place before, so we get the same behavior from our system. But this time, instead of loading all the memory, all the contents in memory, we're actually going to loop over and pipe over the file from one handle to another until there's nothing left to pipe through. At the end, we're going to do similar cleanup. So here we explicitly have to unlock those handles so they're freed up for the rest. And we're going to close the handles. So again, what can we do? We can, again, do an Apache Bench benchmark, same conditions as before. But now the time taken for tests is drastically decreased. Also, the number of failed requests is down to 0. Time request per second is now a threefold of what we had before, and the time per request is also a lot down. Maybe more interestingly, though, if we look at these percentages, like the first 50% came in around 13,000 milliseconds, and the slowest one came in at, well, a bit under 14,000 milliseconds. So the difference is a lot smaller. So if we do the super simple math, and we see the difference between the first 50 and the slowest one, we can say on top we have around 7,000 milliseconds difference in those percentages, while at the bottom we are not even hitting 1,000. So this is like a factor 10 difference in terms of well, stability, basically. So what you can say is you want to aim for stability. You can do that by reducing the amount of resources that you spend on a given operation. How can you detect this? Well, you can log certain things at the end of request. There is a way to get the peak memory usage in PHP. You can simply start logging those out and seeing where the biggest hits in memory are. Same goes for, is there such a thing for CPU? There's such a thing for CPU. Okay, cool. So you can use those things, and what you want to aim for is stability, and then through that you get consistency, and because you now have a consistent performance in your app, you can have predictability, so you actually know what kind of resources you have to give to your application. If we look at this like from a outside perspective, we could say that we have a timeline, and at any given point in time, there are 3 fictional people who are performing various types of requests in our application, and we're using a resource X. It could be memory, it could be CPU, it really doesn't matter. And here you can already see, well, it peaks around 9, and that's, you know, so maybe I'll put a little margin in there, so at peak usage, I'm using 11, maybe. But this chart doesn't show the full picture. Like if you get statistics from your monitoring that you may or may not have, this can tell the wrong story, actually. Because if you look at the same data and you create a stacked line chart, it starts to look something like this. So this is a whole different picture. Like if we capped our memory usage to 11, well, we couldn't nearly hit the spike that we obviously have here. So actually looking at monitoring stuff in this perspective rather than single, like put it in context, is really beneficial in your understanding of what your system actually uses. So it's always good to ask yourself, can this happen to me? And if so, what can we do about it? Well, maybe caching. You know, it speeds things up. Well, I look at caching and I say, caching is like trading a cocktail for a shot of vodka. It sure as hell is going to get me to my goal faster. But caching, or alcohol, just like caching, is often misused to hide problems. So you might want to stay away from it. For instance, you are a news agency, and you're sending out a push notification, like here. This actually happened, by the way. So what happens next? Well, everybody goes to the website, and that's what you're asking for, right? You're saying to people, come see my website. It's fantastic. And we're cool because we cache everything. But then, a cache stampede. Well, what happens when everybody goes to the website? You're not sure if that cache is there, so it might actually be missed. And what happens during a cache stampede is the following. We've got our application, which you can boil down to just being a function, and on a global level, it does something like this. It checks if it has a cached response. If so, it will return the cached response. So here. If not, it's going to fetch the content, or the response in this case. Then we're going to cache it and return that response. But what happens if you have multiple people hitting your application simultaneously? You've got 4,000 people who are all missing that same if statement, after which all those 4,000 people happily move on to the second block, where all 40,000 of us, or 4,000, I don't know, let's ramp it up to 4 million people, are all fetching the response. Additionally, so that's hitting your infrastructure, like the APIs that you're addressing and everything, but also all those requests are hitting your cache because they all get it back, and they all say, well, this is the new stuff, I'm going to rehydrate the cache. So we've actually got a double hit here. That's real dangerous. So how can we prevent this? I don't know, who was in the previous talk? Yeah? Well, Varnish has certain nice capabilities. It can actually combine requests. So in this case, it would be, if this was Varnish, it would get the request. The first request would say, well, do I have a cache? Then, well, no, I don't have a cache. And more people are coming. And we'll just accumulate those requests, and actually just one of those requests will actually hit the backend, and it will return the response and send that to everything who was waiting for that same response. So you can actually prevent such a thing that way. Another way you could do it is actually warm caches before they are hit. It's really good in your system if you're tackling a certain domain, like if you're a news agency, that you know when things are happening or probably are going to happen in your system. For instance, that news agency might have a article was published event, which normally only the notify readers for sending the push notification will receive. But simultaneously, or even before that, we could say, well, let's warm the caches before they're going to hit it. So you're there, ready with the response when they get there. So you can, in your situation, think of ways that you can apply this for your domains. And it's actually, if you use nice and good descriptive events, you can tackle a lot of these. But it's really good to always keep in mind that you're caching for scale and not for speed. If you hide a speed problem, or speed problem, that's not the drugs problem. If you hide the execution speed problem, let's wait for the fight. Okay, if you hide it, like you're actively hiding a problem, then it's sometimes like if that's your go-to strategy, and then your monitoring is going to be all messed up because it doesn't reflect the actual performance of your application anymore, and at random, your TTLs are going to expire, and you see all these weird spikes in terms of load on your actual system. This, again, comes into play when you want to predict what kind of load your system is going to be under. It's like if you hide the true performance of your application, you're never going to be able to make the right assessment for your case. Then again, if you can't speed it up, cache the living hell out of it. Seriously, though. Sometimes you have to be really pragmatic about these cases because you're not always in control. If there's a supplier of data and it's just going to random or maybe change once or twice a day and the API is super slow, you know, we've all been there, right? Just cache it. Preemptively cache it. Store it somewhere else, and in a cron job, just say the TTL here is going to be from now until forever, and then add a cron job which just periodically queries that web server in the background. That way, you'll never hit that. So that's a different way or another alternative that you can use in these kinds of situations. Caching can only get you so far. But if you can't prevent something, you need to facilitate it. So this is where architectural scaling comes into place. The first one I'm going to address is vertical scaling. Here we have our app. Now we're going to do some vertical scaling. OK, that's vertical scaling. So basically, you take that box and you say, well, it has more CPU and it has more mem now, but a server can only be so huge. Like, there are certain things you can't easily scale on. The number of concurrent connections is something that's really hard to scale up. And if you have like Laravel Echo and you run your own node thing to actually serve the sockets, this is something that you're gonna run into if you have a heavily connected systems where you use a lot of WebSockets. Also, it's monitoring hell. You can no longer monitor one system as a whole and really nicely determine where the spikes are. Also, when they fall hard. So like when you have one system, or you have a tiny system in a big box, and that tiny system has a problem, that tiny system can be responsible for taking out your huge VM or your huge server. You don't want that to happen. Also, when you live in one box, updates are not so nice. Updates can be really dangerous. Like when you apt update or apt install a package, you're entering this space of no return. It's like when stuff goes bad, and stuff will go bad at times, and those times it's so difficult to recover. On the other hand, horizontal scaling is a whole different thing. Again, we have our app, and we've got a browser querying that application. And we can, as a first step, we can extract some of the things that we normally have in that one box. Like if you have your Vagrant box, chances are your MySQL database is going to be in there. Well, your first step could be to extract that database into an own API or an own VM. So you've extracted that there, and that load of what the database is actually getting is now separated from the normal processing your application. So we can do the same for caching. We can do the same for queuing. And if we have all these things in place, we can now start to offload work to the background. Well, Laravel has a lot of easy ways to do that. You could just put another instance of that application on a separate VM, and just let that VM be the one who's consuming the jobs. So you can introduce a worker. But still, if we look at our API nodes, like our app, it's one node handling all the loads. So what we want to do is actually have multiple of those, so a bit like this. Already you see there's a lot more networking going on, but there's also another thing, is that the browser, the browser can't know which API node actually to address, right? Domains don't work like this. So we're going to have to use some kind of proxy, and you can quite easily set up a proxy using Nginx or HAProxy, because the majority here is probably familiar with Nginx. I've got the 12-line Nginx load balancing set up right here. So here you can see we're defining an upstream. This is actually where our backend, so that's the actual application that we're hitting. And those server 1, server 2, and server 3 could either be host names that you have defined in your internal network, or they could be IP addresses of the VMs that you want to address. In the second block, we've got a normal server block, which listens on port 80. And when it hits anything in location /, it will proxy that using HTTP version 1.1, and will proxy pass that to the backend. So it's a literal one-on-one mapping from this backend to the other, which is fairly simple. So instead of this, we're now here. So now we have got the browser who's talking to the load balancer. The load balancer, in turn, are talking to app 1, app 2, app 3. They are, in turn, talking to the queue, the database, and caching. And somewhere else is either one or multiple of those workers. So as you can see, it's already quite a lot. So are there downsides to this? Well, absolutely. You know, there's a lot of ceremony involved in getting all these things into place. You've got security updates. So again, you know, every VM that you put out there, you have to support. Package upgrades, networking, firewalls. All these things need to be done on every machine. Solution for this? Use some automation tools. There's Ansible, which is like if you know shell commands or bash commands, it's pretty much that, but then in YAML. Chef and Puppet are also fine alternatives. And if you automate all these things, you have a lot less to care about. Also, it's going to be easier to monitor stuff. Like if you have to watch individual processes, it can be tedious, but now you've got one task per node, so you can look at the node as a whole and see how it's performing, and more easily see where things are going pear-shaped. If you want to get into monitoring, there are things like New Relic or Prometheus, or Munin if you feel a little more old school, and you can quite easily set this up. I know DigitalOcean has tutorials for pretty much all of them. So you can get started with monitoring there. But that's only services or processes and language statistics that you get there. But your application has certain needs or systems it wants to keep in place as well. And those things have more to do with business logic. So what we do at the company that I'm currently consulting for is we actually create status pages for all the services that we use. So, for instance, we have a queuing system, RabbitMQ, and we created some assertions on that system for things that we expect always to be there. So, I want a consumer for flight info. I want there to be, it must be in a running state. It should have less than 100 messages in there. If it goes up, we see a different status. And all these things can quite easily be introduced in your stack. Like, if you create a monitoring page that just asserts things that always should be there, you can deduct very easily where systems are failing or not performing optimally. As an illustration, I've messed around with some of our content importers, so we can actually see, I always expect my indexes for Elasticsearch to be aliased, but there's a content alias which is unaliased, so that's kind of a smelly thing, so we get a poop emoji. The rest is all fine, and when stuff is really getting out of hand, we get a skull, so we know what's going on. So nobody wants to look at a poop all day, so you know your developers are probably going to fix it. If you have all this in place, and you've got the horizontal scaling, you can basically forget about software upgrades. That's pretty nice. You can replace nodes instead. So you just install a fresh installation of a given, like Elasticsearch, you just put a new node there, or a Redis instance, you just put a new node there. And you swap that internally in the network. So you don't have that problem of being in that weird spot with software upgrades no more. That makes it so forgiving. Like, I tend to mess up my Vagrant box a lot, and I'm super grateful that I can just destroy the thing and build it right up. And that's nice for development, but you can apply those same ideas and the same concepts. You can apply that to test production or whatever kind of environment you have out there to actually deliver your application. One constraint, though, is that applications need to be stateless. So they must be a processing unit. But what's the state? Well, it's basically that you need to centralize storage. So if somebody uploads it, you don't upload it to your local disk, but you upload it either to S3 or Rackspace or whatever, or a central data node that you've got in your network. And you need to deal with all your session stuff. And that session stuff, because you're all using Laravel, is super easy. Like on Ubuntu, it's basically a 3-line, like add a PPA, update your apt cache, install Redis server, and you're good to go. Like all you have to do besides that is put the driver on Redis, and you're done. Everything that's in Fly System is already available for you in Laravel, so all your files can already be in the cloud. So those two things are the major things that you want to think about when you want to create stateless applications. And I'm only going to spend 4 slides on this because it's so damn easy in Laravel. So, but in the end, there is no silver bullet. As I said, with caching and that stuff with push notifications, it was really specific to the business. And for your cases, it's going to be as well. Also, in the scope of everything that's related to scale, you can see it addresses a whole range of things. It's basically a death by 1,000 cuts. What you can do is make tiny experiments. Experiment with caching. Check which operations consume the most memory. Try to optimize those. And when you do, go for big wins first. Quite recently, I've been in a situation where we had a multi-gig Elasticsearch cluster, and a 20 megabyte data set was bringing that cluster down every 5 days. We tracked it down, and it was a memory issue within our usage of Elasticsearch. And a couple of hours of research, and then maybe an hour or so of writing an implementation for it, made sure that our Elasticsearch cluster was no longer failing. So these things, you want to go for big wins first. There's a whole bunch of stuff that you can research, like optimizing your Nginx setup. Do the same for PHP FPM. Who regularly revises their PHP FPM configuration? Who has consistently, not so much traffic, or the same traffic as their development box? Probably nobody, right? It's really good to tweak that to see how your application responds in certain configurations, because it can really affect your performance. Dive into monitoring, dive into caching. Varnish is a really great tool, but it also has its quirks, and the VCLs are kind of tricky sometimes. Everybody who saw the previous talks can probably agree on that. There's a whole bunch of talks that are concerned about stateless applications. There's a lot to it. Look at server automation, Ansible, Chef, Puppet, all these things. These are just a handful of things that I've researched in order to apply this, all these ideas in the real world, and they've really been helpful for me. So I hope now that you have a good grasp of how wide this field is, and that you might have seen some things that you say, well, maybe I can apply this for my projects. I know certain parts of my application aren't performing. You can narrow that down and attack that problem there. So I really hope you can take that home and make use of it.
I'm curious if that Nginx configuration, first of all, works properly as a load balancer, or it was just a proof of concept?
It can act perfectly fine as a load balancer.
If you're only defining the servers as the upstream variable, it will always probably choose the first one, and only when the first one is full of requests and can't respond, we'll go to the next one. Or am I wrong?
By default, it does a round robin, so it'll actually rotate. There are different algorithms that you can use. You can use IP hash, or you can, if you have session difficulties, you can use sticky sessions. But I would much rather spend time making sure I don't need sticky sessions, because that means your application is not stateless. So basically what you can start out with, if you need basic load balancing, you don't need to introduce some hefty tool into your stack. You can start slow like this. Then if it becomes a bottleneck, you can quite easily convert that same configuration in something that matches it in HA proxy. And like, if you still have problems there are also hardware routers which do the same. And if there's a problem there, then it's an ops problem, not a developer problem anymore. So
okay,
there's always an out.
Thank you. You also answered to my second question, if that load balancer can't actually get to be the bottleneck by himself. So by using hardware, you can probably just
eliminate it. Yeah, and you can also do DNS round robin, which is mostly done for, like, CDNs do that to find the nearest one. It does some of that offloading or some of that stuff because it's DNS and wants to, get the shortest route, so or like the one that first picks it up. But that means if there is a large quantity of your customers in a particular area, then the load there is going to be higher on that piece of your infrastructure. But it is something that you can look into. Thank you for your time.